Hello, and once again, welcome to Physics for the 21st Century. My name is Greg Perugini, and today we're going to talk about collisions. Now, if you remember in our previous topic, we looked at momentum, which is mass times velocity. Momentum being a vector, velocity, of course, is a vector, and mass is a scalar. We noted that momentum is conserved. In a previous topic, we also talked about the fact that kinetic energy and energy is conserved, and it can be switched between various types of energy. Well, we can use these facts to solve problems for collision. Since momentum can be modeled as a vector, we can talk about inelastic collisions and elastic collisions and have various equations to solve for problems involving collisions. Now, an inelastic collision is when we have stick, where an object comes, maybe an object's coming up in this way, this object's coming that way, and they both stick together as one big object. That is inelastic. They are not bouncing off of each other. They're sticking together. Now, an elastic collision is a collision like a billiard ball, and we'll do a problem like this, where ball A hits ball B then goes down here, ball A goes this way. Now, we can use vector algebra to solve for these in each different position, knowing that momentum final equals momentum initial because it is conserved. So let's look at elastic collisions first. Elastic is where they bounce off of each other. Where if you look at this little diagram here, you have one ball colliding with another, and they separate out after the collision. Now, this shows the fact that, depending on the velocities, of course, of each of these balls and the mass of each of these balls, there's going to be a different outcome, as you might expect. Well, given the equations for momentum being conserved and for kinetic energy, they're in the book, and we don't need to solve for those because we have them right here. We can solve problems where, if we want to talk about mass being at rest in one dimension, then of course the velocity of the second ball is going to be equal to 0. We can do a problem like that. Let's do that. Okay, let's say that we have a ball. It's 2 kilograms. Draw it down here. 2 kilograms and 5 meters per second. It's going this way. Collides with a ball that is 1 kilogram, and it is at rest. After collision, velocity of 1 and velocity of 2, what would they be? Well, we can use this equation here. So the velocity of ball 1 final is equal to the mass of ball 1, 2, minus the mass of ball 1, mass of ball 1 plus the mass of ball 2, times 5. Now I could do this second equation, but we know the velocity, since it's at rest, that's going to be equal to 0. So the velocity of the first ball is going to be something like 1/3 times 5, 1.67 meters per second. Velocity of ball 2 final is going to be equal to 2 times the mass of ball 1, 2 times 2, over mass of 1 plus mass of 2, times 5. And what's that equal? That equals 6 2/3 meters per second. So that answers that question. But in elastic collisions, where they bounce, momentum is conserved in perfectly elastic collisions. And so is kinetic energy. Because the before kinetic energy is what? 1/2 mv squared, which is 1/2 times 2 times 5 squared. And that equals what? 25 joules. That's the before kinetic energy. The after would be for ball 1, 1/2 times 2 times 1.67 squared. That's going to give me about 2.8 joules. And ball 2, 1/2 times 1 times 6.67 squared, which will give me about 22.2 joules. And looky there, adding them both together gives me 25 joules as well. Kinetic energy is conserved. Now what if, let's do another type of example of this type of collision in one dimension. This only holds for one dimension. What if that second ball is quite a bit heavier? 2 kilograms going at 5 meters per second hits a 5 kilogram ball at rest. Well, again, using those equations, velocity of ball 1 final is equal to 2 minus 5 over 2 plus 5 times 5 gives us about a -2 meters per second. This ball, after collision, is going in this direction. What's happening with ball 2? Two times 2, 2 plus 5 times 5, about 2.9 meters per second positive. Now, as an exercise, you can verify that this also obeys conservation of energy, just like we did with the previous example. But you could see what happens when this is a heavier ball. This ball is going to ricochet back, and then this ball is going to go in that direction. Let's do an example now of 2 dimensions. Now, if we talk about in 2 dimensions, kinetic energy is conserved as an isolated system, but if we define it, just like in that example that you see there, you could see that we could define a system where energy is not conserved. Let's do an example then. I have a 2 kilogram ball going at 10 meters per second. It's a 2 kilogram ball at rest. This ball here, let's call this ball 1, goes up here at a 30-degree angle at 5 meters per second. So we want to figure out the angle, and we want to figure out the velocity. So, if we look at this, we know the initial momentum. We also know initial momentum final is equal to a momentum initial conserved. I can figure out what's happening in this x direction right? We know initially what's happening in the x direction, right? This ball's at rest. There's no momentum happening except for that ball. P equal mv, 2 kilograms times 10 meters per second gives me, of course, 20 kilograms meters per second. So, the combination in the x direction of this vector here and ball 2 vector in the x direction, okay, it also has a velocity in that direction. They must equal 20. So, 20. The momentum of the ball in the x direction is 2 times 5 times cosine of 30, right? The 5, this vector, the portion that is in the x direction is cosine of 30 times 5 plus 2 times the velocity of ball 2 in the x direction. So this is 20, 8.66 plus 2 velocity of 2 in the x. Velocity of 2 in the x is equal to 5.67 meters per second. What's happening in the y direction? This is in the x. So I'm going to write this down here. So we know the velocity of ball 2 in the x now must equal 5.67 meters per second. Okay? Now, what's happening in the y direction? Well, the initial in the y direction is what? There's nothing happening in the y direction. The momentum initial in the y is equal to 0. So whatever is happening positive must negate whatever is happening, and the addition of these two must equal 0. 0 is equal to momentum of the first one in the y direction, sine of 30, times 5, times, of course, the mass, P equal mv. Remember that. Plus 2 times velocity of ball 2 in the y direction. We're solving for that. And those two together must equal 0. What you end up with if you do this is 5 plus 2 velocity of 2 in the y equals 0. Velocity of 2 in the y is equal to, of course, negative 2.5 meters per second. So we know this part here, let me see if I can draw this in another color, is negative 2.5. The strength is 2.5. And we know this part here for this ball is 5.67. How do I get that angle? Tan inverse of 2.5 over 5.67. The angle being, I'll let you calculate it too, you should get 23.79 approximately, 23.8 degrees. So the answer to the question here, let's go with 23.8 degrees. So, what is the velocity of ball 2? Well, if we have both components, we can do the 2.5, I'll start with the y, 5.67 squared, starting with the x, plus 2.5 squared to give me the magnitude of this velocity. And the answer then would be about 6.2 meters per second. So, based on conservation of energy, if this ball is going at 10 meters per second and strikes this ball and goes off at 5 meters per second at 30 degrees, what must happen to ball 2 is that it goes off at 23.8 degrees below the positive x-axis at a rate of 6.2 meters per second. So, that's an interesting problem in and of itself, but let's also look at some another piece of this. Kinetic energy. Before, if you remember, the equation for kinetic energy is 1/2 mv squared. The kinetic energy initial is equal to 1/2 times the size of the ball times the mass of the ball, 2 kilograms, times its speed, okay, 10 meters per second, squared, gives you 100 joules. What is the kinetic energy after? The final kinetic energy. Well, our first ball we defined, if you remember, we defined this going at 5 meters per second. Remember, kinetic energy is a scalar. 1/2 times 2 times 5 squared. And then you have to add in the kinetic energy of the second ball. 1/2 times 2 times second ball going at approximately 6.2 meters per second squared. If you add those two together, you get 63.4 joules. Not like the first examples we did. There is a loss of energy. Whether it be by friction or sound or deformation, whatever it might be, a loss of energy in the system. So kinetic energy is conserved, but it may be transferred in another form. In a sense, we have a little bit of an inelastic condition. What is an inelastic? Again, we stick together, as in this example. Ball 1 and ball 2 hit, and they stick together. Now, it must be consistent with conservation of momentum. In one dimension, we could look at this equation. Often you see this in 2 dimensions. Let's take a look at it. Like so. We're going to have a collision here. We have a car, 1,000 kilograms, and a truck. It's 2,000 kilograms. The truck is going at 2 meters per second. The car is going at 1 meter per second. So they each have their momentum, and it is where they both stick together. Inelastic. What is the velocity of this resultant mass? Well, before, in the x direction, we have what? Just the car, right? We have, I'm sorry, I defined this as a 3. Can't read my own writing. 3 times 1,000. Momentum is 3,000. It's in the x. In the y, it's just the truck. 2 times 2,000. P equal mv. It's 4,000. Now, knowing your vector algebra, of course, we can't just add those together. Those are strengths. So the momentum before has an x and a y component. $3,000 squared plus $4,000 squared. Take the square root, and it's going to give me 5,000. This vector here, the momentum of that vector here is 5,000. So, if momentum equal mv and it's 5,000, we can figure out the velocity knowing that they both stuck together, so it's a total mass of 3,000. Velocity is about 1.6 meters per second of the resulting mass. Now, if you remember on that equation before, we can look at this as well in the same way. We can think of the kinetic energy before. What about kinetic energy? Well, the car has a kinetic energy of 1/2. Write that down, kinetic energy 1/2 mv squared, right? 1/2 times the mass times the velocity, 3 squared. And the truck is 1/2 2,000 times 2 squared. And that is 4,500 joules. And that is about 4,000 joules. Total of 8,500 joules. After, this is before. After they both stuck together, one-half times the mass, okay, and the mass is 3,000. Velocity, if you remember, we calculated it out to 1.7. Total is there is a loss of about 42.65 joules. The before does not equal the after. Inelastic collisions very possibly are not perfect. There's going to be a loss. In this case, you can visualize the loss, right? Of course, it's going to be heat and friction. So, in summary, it's a very detailed subject we have here. We're talking about 1D collisions. You can use those equations. For 2D, make sure you separate your vectors and treat each component independently. Know your vector algebra, particularly when you're going to be doing an inelastic collision, much like this car and this truck. And look online and look in the book for examples. And good luck.